In this presentation, we'll look at several examples of the frequency response of a second-order system with base motion. And this system is shown here. We have a mass attached to a spring and a damper to a base which is moving. The motion of the base is given by x, and the motion of the mass is given by y. So here the input is the displacement x of t, and the output is the displacement y of t, the motion of the mass. We can find the equation of motion of this quite easily. The equation of motion is, of course, the mass times the acceleration equals the sum of the forces, or my double dot equals Fc plus Fk, where Fc is the force produced by the damper, and Fk is the force produced by the spring. As we found before, we can find those quite easily. The force from the damper is minus c times y dot minus x dot, and the force from the spring is minus k y minus x. So we can simplify this equation of motion to my double dot plus cy dot plus ky equals cx dot plus kx. We've moved all the x terms to the right hand side and kept all the y terms on the left hand side. We'll now find the transfer function, and for this, of course, we set all the initial conditions to 0 and we Laplace transform the differential equation. And then after a little bit of algebra, we'll find the transfer function is as follows. Y of s is equal to g of s times x of s, where g of s, the transfer function, is cs plus k divided by ms squared plus cs plus k. So this will be the transfer function for all the systems that we'll look at in this presentation. The first thing I want you to examine is the DC gain of this transfer function. And remember how we find the DC gain. We simply set s equal to 0 in the transfer function. Doing that, we find g evaluated s equals 0, and that will be k over k, where k is the stiffness of the spring. And of course k over k is 1, so the DC gain of this system is 1. And the question I want you to consider now is, does the fact that the DC gain equal 1 make physical sense? Let's take a look at this. Let's take a look back at our system and ask the question, what happens if we do a step displacement in x, the base? What will happen to y as a result? Now physically, we can't really have an instantaneous displacement in x of t, like a step is basically describing. After all, in a step, we go from a value of 0 to a value of 1 in an infinitesimal amount of time. And this physically can't happen for our base. It can't move that fast. But let's suppose that we have something very close to a step, so that it's moving very quickly from a value of 0 to 1, so quickly that we can treat it as a step when we think about the problem. So here we have a graph versus time of the base motion, given by x, the purple line, and the motion of the mass, given by the red line. That's y. And what you'll notice is we start off at rest with the spring at its natural length L. And then the step occurs. And when this step occurs, what will happen is x will move quickly, but the mass, given by the red line, won't move so quickly. And so the spring becomes compressed. Then after some time and some oscillation, the mass will settle down, and the spring will return to its natural length L. When it does so, we find that y has moved the exact same amount as x. And that's what it means to say the DC gain is equal to 1, that the steady state value of y is equal to the steady state value of x. So it does make sense that our DC gain is equal to 1. The next step in analyzing this problem is to put our transfer function into a standard form. So recall our transfer function was cs plus k divided by ms squared plus cs plus k. Now the denominator, the standard form for that, is the one we studied for second order systems. S squared plus 2 zeta omega n s plus omega n squared. we'll put the numerator in the following form: the DC gain, KDC, times tau s plus 1 times omega n squared. And we can always take CS plus K and put it into this form. Now the parameters in our standard form can be related to the physical parameters C, K, and M through the following relations. The DC gain, of course, is 1, and the natural frequency omega n is equal to the square root of K over M. We can find zeta from the equation zeta omega n equals C over 2M. And then finally, the tau in the numerator is given by C over K. We've put the transfer function in this standard form with these new parameters, DC gain, tau, omega n, and zeta, so that we can better understand how the system responds in terms of the parameters that appear in the transfer function. Now let's find the poles and zeros of this transfer function in terms of these parameters. The poles are given by minus zeta omega n plus and minus j square root of 1 minus zeta squared omega n. And 1 minus zeta squared square root omega n is what we refer to as omega d, the damped natural frequency of the system. Zeta omega n is equal to 1 over the time constant of the pole, which is labeled tau sub pole. The zero of the transfer function is given by minus 1 over tau. And of course, tau was C over K, so this is minus K over C. So where are the poles and zeros in the complex plane? Well, I have them marked here. The poles are at minus zeta omega n plus and minus j omega d, and the zero is at minus 1 over tau. And I've drawn this with zeta being about 0.8. And of course, this system, we know, is Bibo stable, since all the poles are in the left half plane. So what does the frequency response of this system look like? Well, I have it plotted here. The dashed line shows the asymptotic frequency response that we would get by following the construction equations. The curved solid line shows the actual frequency response. And what you see is that we have a DC gain equal to 1 for this system, and then at the frequency of the zero, 1 over tau, we have an increasing value of gain, and the slope there would be plus 1. That continues till we get to the frequency omega n, where the slope would change to minus 1. I've exaggerated the peak in this frequency response because it's more than likely that omega n would not be so separated from 1 over tau, and so the peak is not going to be as large as what we see here. Another important thing to point out is that at high frequency, the gain is quite low because we have the minus 1 slope. So just to remind you, the reason why the frequency response has this particular form is because we have 1 zero at 1 over tau, and we have 2 poles at a frequency of omega n, that is their distance from the origin. And therefore, the shape is as shown. It would be a good idea for you to reproduce this result. Take the transfer function given and use the rules to sketch it. See if you obtain a curve which is similar to this. Let's now look at an application that has this transfer function, and the application is an automobile suspension. So our mass that's moving, m, is going to be the car body, and x, the displacement input, is going to be the road. And of course, these two are connected by the suspension, which we model as a stiffness and a damper. So in this model, what we want to do is we want the tires to follow the road surface so the driver has a feeling of control. And so what that means at low frequency, we want y to be the same as x. But then we don't want the car body to feel the road's roughness. So that means at high frequency, we want Y to ignore X. That is, the vibration X should not pass through to the car body vibration Y. So number 1 means that we want the low frequency gain of the system to be 1, so that the car body follows the road for low frequency inputs. And number 2 means we want the high frequency gain to be very small, so that the car body does not excessively vibrate in response to the roughness of the road. Those goals are translated to the frequency response curve for the automobile suspension system, as shown here. At low frequency, we want the DC gain to be 1, so that the car body motion tracks the road's motion. At high frequency, we want the car's body not to respond to the roughness of the road. That is, we want the gain of the transfer function to be very low. And this is achieved by having the -1 slope. So the task of designing the auto suspension's stiffness and damping can be seen as trying to pick the corner frequency, where the slope changes from 0 to -1, to pick that corner frequency appropriately, so as to get the car to follow the low frequency road motion and to reject the high frequency road roughness. You can see this behavior of the automobile suspension in this video clip. Now we'll look at another application with exactly the same transfer function. And this application is a vibration isolation table. And a vibration isolation table basically seeks to isolate the top of the table from the vibration of the floor. And this is used for very sensitive processes, often in laboratories, but also devices essentially like this are used in semiconductor manufacturing, where we can't stand any vibration where the photolithography is taking place. So here's the model of the vibration isolation table, and you'll notice it's very similar to the automobile suspension. We have x of t, the ground's vibration, and this would be due to all sorts of extraneous machinery, cars, people moving about, causing the ground to vibrate. Then we have the suspension, which is given by a stiffness and a damping. And then we have the mass of the table itself, and its motion is given as y of t. Now this system has the same transfer function as the automobile suspension, but in fact, in some ways it's quite different. And it's different in the way that it's engineered and the requirements that the transfer function have in terms of the frequency response. So let's take a look at the frequency response for the system. Now the DC gain, of course, is going to be 1 again, just as before. And of course the high frequency slope is going to be -1 on the log-log scale. The trickiness here to doing the vibration isolation table problem is to try to get the corner frequency low enough, because ground vibration can be coming in at fairly low frequencies, especially the vibration that's coming from, say, cars driving by or doors closing. So what we need to do is we need to have that corner frequency quite low. Now think about the way to achieve that. That corner frequency is essentially the natural frequency of the system, omega n, which is the square root of k over m. We're limited in terms of how small k can be made. Typically these tables, the k is achieved by sort of an air or pneumatic system. And it can be low, but to get k very low, what we need to do is to make the table massive, to increase m, and that will lower the natural frequency of the system, lowering the corner frequency here, and yielding greater vibration isolation at the frequencies of the disturbance. Now in just a moment we'll look at the performance, the frequency response performance, of a commercial isolation table. But before we do that, we have to talk about the way that performance is given. And here's the problem. If we conduct a test, we can't exactly vibrate the ground underneath one of these tables. So the way the test is done is not to use a displacement input x of t, but to rather use a force input on the mass. So that's shown in this diagram here. The input will be F, not x, and the output will be the vibration, y. This gives a different transfer function than if x was the input. And the transfer function then is going to be 1 over ms squared plus cs plus k. You'll note that there's no zeros to this transfer function. Because of that, we have a slightly different frequency response curve. The DC gain of the system will be 1 over k. The corner frequency will still be omega n. But now, because we don't have a zero in the transfer function, the high frequency slope will be minus 2. So this is different than what we saw before, where because of the zero, the high frequency slope was minus 1. Before moving on, let me just recap the situation here. The reason why we have a different transfer function is because we have a different input. And the reason why we have a different input is because it's simply difficult to do the test on a commercial isolation table using the ground vibration as the input. But nevertheless, the commercial isolation table is designed to isolate from the ground, not from an applied force to the table. It's just that the applied force to the table is used in conducting the test, since it's easier to conduct the test that way. Shown here is the frequency response of a commercial isolation table, and this is the black line. The red line is the line for an ideal rigid body, and that's the comparison that the makers of this table are wishing to make. Now, the ideal rigid body's transfer function is 1 over ms squared, and this transfer function has a slope of minus 2. So the makers of this table are showing that their table acts like an ideal rigid body up to a frequency of a little over 100 Hertz. They're showing you that it achieves a minus 2 slope over this region of frequency. The next thing you should note is that the corner frequency is so low it does not appear on this graph. It's somewhere below 10 Hertz. We know at very low frequency the graph must have a slope of 0, and the corner frequency changes this to a slope of minus 2. We just don't know how low that corner frequency is. And that's actually important for understanding how well this table behaves in isolating versus ground vibration. Finally, let's discuss why this transfer function doesn't have a minus 2 slope at high frequency. It appears to level off somewhat, and there appears to be some resonances or something happening around 200 Hertz. This is caused by the fact that the table mass is really not a rigid mass. It has its own flexible modes, and at some point those flexible modes are going to start affecting the frequency response. The designer of the table wants to make the table as stiff as possible, so as to try to push those modes higher and higher in frequency. But there is always going to be some limit to that for a large table. We've now seen two practical examples where base motion is exciting a mechanical system. In our next presentation, we'll look at an experiment with base motion exciting a system.